Welcome to the lecture for Chapter 28. We're going to talk about the evolution and distribution of galaxies. So we're going to start off by considering how galaxies can change when they collide with each other. Here we have an example of the collision of galaxies as shown from telescopes, both ground-based and space-based telescopes. The idea here being that the ground-based telescope is lower resolution because of the interference with the atmosphere, and here we can see the much higher resolution, clearer picture of these colliding galaxies. We see phenomena we talked about in previous chapters. Regions of blue representing young, hot, short-lived stars that are being formed because of highly energetic pockets of gas in the galaxy. Okay? And it's so clear. And we also see regions of gas, dark, thick molecular gas covering large sections of the colliding galaxy. And what's more is we see the shape, which is clearly not a spiral galaxy, but is clearly a dynamic shape showing the galaxies fusing together just like you might imagine whirlpools merging in a fluid. Okay, so let's stress the importance of distance and time, because we see here in this image of galaxies at very far distance that we're looking first of all at the true color image of these galaxies. So we are seeing that these galaxies are accounted for, are corrected for their incredibly far distances. Because otherwise, what color would they all appear? They would all appear red. But that is not their true color. That is not the light that they emitted. They appear red to us because they're moving away from us so quickly that the light is affected by the Doppler effect for any wave, and specifically it's at a very extreme level for these astronomically huge speeds of distant galaxies, and they would all appear red. But that's not the case. We've corrected for that wavelength, and we're seeing galaxies that are blue, some that have colors throughout the visible spectrum and thus appear white, and primarily, you know what we don't see? Red. Instead of it being dominated by the Doppler effect, by the so-called red shift, good name for it, instead we see blue and white. Why is that? Because when we look this far away and we look at these distant galaxies that are 12 billion years old, okay? We're seeing very young galaxies because 12 billion years ago, there were no old galaxies because the universe itself is only some 14 billion years old. So looking at 12 billion year old galaxies means we're looking at galaxies that are only 2 billion, give or take a few 100 million years, old. And when we look at these young galaxies, we see very active galaxies with lots of hot, high mass star birth. And how do we know that? Why is that consistent with everything we've discussed? Because they are blue and they are white and they are not red. Because if we did see a true colored red galaxy, that would be a galaxy of old stars that have lasted for a long time. And all the young stars have burnt out. And all that's left, all that remains, are the old red stars that live for 10s, 20s, 30s of billions of years based on models. Of course, they haven't had a chance to live that long because the universe itself is not that old. Okay? So this is an idea that an early population of galaxies, like the one shown in this image, in this figure, represent what galaxies looked like earlier in the saga of the universe. A time when galaxies were all young and they burned hot and bright and blue, or at least bluer. Okay? Furthermore, we can look at the very limit of distant galaxies. What about the first galaxies? What are some of the oldest galaxies we can see? And this is an example of looking at a galaxy that is 13.2 billion years old. Because we are looking back 13.2 billion years in time. We are time traveling back into time because we are looking at distance that light would have taken to travel 13.2 billion years. And we see this galaxy here, zoomed in. Okay, we see this very distant galaxy. We see that it is not like modern galaxies. We see that it doesn't have a spiral structure. It is small, And that is going to be one of the key takeaways about these old galaxies. At the very extreme level, they are incredibly small. They're what we would consider dwarf galaxies in the current population of galaxies. And they're fundamentally different in terms of not being elliptical or spiral in shape. They're just the early stages of star clustering, of mass clustering that we can recognize in the universe. All right? So when we look at these very distant images of galaxies, one thing becomes apparent that I said before, a word that I think describes the evidence that we see with distant images of galaxies is they are irregular. They're not easily categorized into the types of galaxies that we would see near us. Because the galaxies, like in our immediate neighborhood, in our local group of galaxies, or even other large groups of galaxies, but ones that are only a couple billion years away in terms of how fast light travels, or those that are even just a few 100 million light years away, thus only looking back in time a few 100 million years. Well, those are contemporary galaxies. Those clusters are composed of contemporary galaxies with our own Milky Way, and we see a mix of elliptical and spherical galaxies. All right, spiral. We see a mix of elliptical and spiral galaxies. But we don't see that with the distant galaxies. We see incredibly strange things. We see galaxies that are mostly irregular. We see lots of galaxies that seem to be in the process of merging together because they're all packed together. They're collapsing in on each other. And this picture from the Hubble Space Telescope, taken over an 11-day long exposure, is a wonderful example of that, because although there are some spiral galaxies, this image is full of galaxies at various distances, and there are ones that are crashing together, have very unusual shapes, right? That are in the processes of merging. And that is so characteristic, so representative of what's really out there. And the reality is that it is not a universe of just spiral and elliptical galaxies, because it's a universe of time travel. Because when we look at galaxies, we're looking at galaxies over different eras, fundamentally. And thus we see the trend if we're able to decipher it. Okay? So more about these early galaxies, previous galaxies, the type that existed before. We can see galaxies under construction. Why do we say they're under construction? Because they're so much smaller. We see groups of galaxies that are only about 2,000 light years across. Okay? So this is the first time in this lecture, the first slide, that we've really seen this idea about how small some of these early irregular galaxies were. Because compared to our own galaxy that's 100,000 light years across, 2,000 is tiny. It's a 50th of the size. And that's a 50th of the size in the diameter. The actual volume would be, well, potentially 50 cubed, because the relationship between length and volume, you raise it to the third power. And so what we're seeing here is we're seeing galaxies that are so much different, so much smaller, so much more primordial. Early primordial galaxies must have somehow formed the galaxies we see today, the elliptical and spiral galaxies, these final endpoints of galaxies. Furthermore, we see some of the smallest, truly smallest galaxies that aren't 2,000 light years across, but instead 850. 500 times smaller than the Milky Way galaxy. So at the extreme level of both technique of even recognizing and resolving images that are so small and hard to detect, we see compelling evidence that the further back we look and the techniques that we use to look back further and further, the smaller the galaxies become. And so we really seem to be seeing a trend that the mature giant galaxies and the distribution of galaxies is an endpoint of something that was a long time coming and started with very small clusters of galaxies and started with very small galaxies as well. Galaxies that were only 500 times smaller than the Milky Way galaxy. Something that we would barely even classify as a dwarf galaxy today, even if we even were to classify it as a dwarf galaxy. So, that's the trend. That's the behavior of galaxies, from smaller to larger, from irregular clouds to definitive shapes that we call elliptical and spiral. Okay? So that's definitely the process of growth of very small clouds of stars that we call irregular, distant, young galaxies, to the types we see today that we can categorize that seem to be so dominant in terms of the population of galaxies over the last couple of billion years. It's amazing we can group together a couple billion years, but that's just the scale that we're dealing with here in terms of time and space and distance. But beyond that, beyond just smaller galaxies leading to larger ones, there's the inevitable interaction between them. And there are so many examples shown in this beautiful gallery of interacting galaxies. It is such a common phenomenon that is so incredibly dynamic and leads to so many different results, as you would imagine with a system as complex as that, composed of billions of individual moving pieces. And with modern computing power, with the computational achievements that we currently have in the modern day, we can get an idea of how this works. We can actually simulate the behavior of galaxies. And one thing, and I've said this before in previous lectures, one result that seems to have a lot of credence to it and that the mathematical models suggest when we run these very long simulations is that when galaxies do crash together, they form elliptical galaxies. And when I say galaxies crashing, I guess it's best to think of that as spiral galaxies, the galaxies that have been around for the last 5 billion years. And when they come together in this complex way, they end up losing their spiral shape. And the result is a dispersal of energy, a loss of interstellar medium, of gas, and an end result of the conditions that only facilitate the continued life of the longer-lived red stars, thus the large elliptical red galaxy that still has a core, still has a leftover supermassive black hole at its center, one of which may be the merger of multiple supermassive black holes that have all gravitationally danced, circled, and become one, but still not a spiral galaxy. Okay? Now, to be clear, this isn't the only idea that astronomers have based on the evidence of elliptical galaxies. They also really think, and have every reason to think, the elliptical galaxies also can be formed separate from the collision of spiral galaxies, and can exist in just places where there was not very much angular momentum to begin with, not very much rotation to begin with, and the initial conditions for a spiraling galaxy facilitating active young star birth within its spiral arms that are denser than the rest, that never formed, and a more uniform, homogeneous elliptical galaxy formed. And I think a good reason astronomers think that there are multiple paths to the formation of elliptical galaxies, maybe they are more the natural endpoint of galaxies, is because there's so many of them. They are so incredibly common and are situated and are found in such larger clusters than spiral galaxies that they seem to be the most likely form of galaxy. Furthermore, we have evidence of galaxies interacting in ways that really that can only be explained by not the visible colliding of galaxies where you say, look, we've happened to capture them, where you can clearly see, like the opening slide, you can clearly see two spiral galaxies colliding. Just look at its shape. Instead, there's more indirect evidence of previous activity. Because here's a spiral galaxy that is full of dust. But spiral galaxies are almost never full of dust. So why would there be a spiral galaxy full of thick, basically molecular clouds, cool clouds of larger molecules? Well, that dust had to come from somewhere. Probably from the cannibalism of another galaxy. The gravity of the spiral galaxy probably pulled another galaxy in, and we're seeing the leftover remnants of that activity. Or this image here is so remarkable and such a great throwback to the previous chapter when we talked about active galactic nuclei, otherwise known as quasars. We see two clear cores that haven't yet formed. It's that final dance of two supermassive black holes before they become one. Here we see just how we can have lots of blue star formation when the galaxies interact. Okay? Colliding, lots of heat exchange, lots of friction, lots of collisions that would not have taken place at the scale of atoms and molecules if these two huge structures had not interacted. That energy goes somewhere, and then energy goes to hotter gases, it goes to spreading out energy, and then can lead to the formation of stars, because that hot gas can condense regions, forming higher mass stars than otherwise would have formed. Okay? And we can see collisions throughout the history of the universe in distant clusters as well as closer ones. We can see it in clusters of galaxies that are 5, 10 billion years away in terms of how far light travels. Or we can see it in clusters that are only 50 or 60 million light years away. Here's another example. Okay? And here's Edwin Hubble looking through a 100-inch telescope at Mount Wilson. All this formational understanding of galaxies. Okay. So, the reason, to be honest, that we just saw Edwin Hubble was because what he did in terms of deriving Hubble's law, of coming up with the idea that the redshift could tell us distance, and even leading to the fundamental idea that the galaxy is expanding and started with the Big Bang. All of that began with looking at the local group shown here in this image. And that's the local group of galaxies. Because that was, first of all, if you recall, how it all started in terms of Hubble's exploration, was understanding that these nebula were not nebula, but were in fact separate galaxies as big as the Milky Way itself. And although you may think that the local group is the worst group of galaxies for studying Hubble's law, and you'd be correct, it still was the beginning. Okay? But now we think of the local group in a different context. We think of it as the group of galaxies that we're interacting with, that we're eventually crashing into, that is composed of lots of little dwarf galaxies, right, like LMC and SMC, that are eventually going to crash into our Milky Way and feed the energy of the galactic core of our own galaxy, maybe even jumpstart or fire up our own supermassive black hole. All of that is great. But what's interesting about the local group is that it just shows us one little snapshot of the universe. It just gives us an idea about how galaxies are situated, how they're grouped together, and how our own galaxy is no exception. How there's clusters of galaxies throughout the universe. And indeed, we can see clusters of galaxies, some relatively close, at only 500 million light years away, and some really famous ones like the Coma cluster that are further at about 320 million light years away. But you know what both the Virgo cluster and the Coma cluster have in common? And even though one is over 6 times further away from us than the other in terms of galactic distances, in terms of course, billions of light years, or in this case, millions of light years, well, it's that they're both relatively close. So notice here that we've shifted gears from our discussion from the early bit of the chapter, and we'll hopefully tie it all together. My goal is to tie it all together. But we were talking about the evolution of galaxies and how galaxies that are tens of billions of light years away are quite different. But here we're saying that we're looking at clusters that are only tens, 20s, or hundreds of millions of light years away. But the reason is because we want to get an idea not just about how galaxies have changed from a regular through collisions and mergers to spiral and elliptical, but also how they fill the space between themselves, the space of the entire universe itself. Because if we see clusters like Virgo and Coma, well, that begs the question. If there's clusters, then that means that galaxies aren't evenly distributed, right? It must. So if there's clusters, there also must be, what's the opposite of a cluster? A void. Okay? At least that's the terminology astronomers use. I guess you could call it a gap. It's everything between the clusters. And indeed, that's what we see. And one thing I want to point out, and that the book points out well, is that if we're going to make this argument going from relatively close clusters of galaxies like Virgo and Coma and tie it in with the overall structure of galaxies that includes those strange young galaxies that are 8, 10, 12 billion light years away, then we need to make a compelling argument about how we can even know or see or understand galaxies that are so far away. And one bit of that, one important piece of the puzzle, is gravitational lensing. And I know this might seem divorced or separate from the other ideas we're discussing here, but what it is that it's just a method, a wonderfully complex method of observing light that's really far away. Because Einstein's general theory of relativity that says that the time-space continuum itself bends under the influence of gravity, and we had a lecture on this and a chapter on this topic, and it's a lot to take in. But that amazing theory from 1915 tells us that light bends when experiencing large condensed regions of mass, which means we can see things from, first of all, multiple points, and second of all, further away than we would otherwise. Because if we have a very distant source of light, like a quasar or an early irregular galaxy, one of those active blue galaxies from 10 billion years ago, well, that light on its path out into space and passing past our own lonely planet, well, it may have passed past some other source of gravity, like a galaxy or a cluster of galaxies. And that big source of gravity bends the light. And it bends the light in such a way that, first of all, the light reaches us from 2 separate points from our point of view. Okay, and you'll see examples of that, because if that sounds confusing, that you'll see pictures in just a moment about showing how light looks like it's coming from different places, and that's just because of this bending of light. But it also amplifies it. And it allows us to see things that we wouldn't otherwise, because in bending the light, it's focusing it. That lensing term is not used superfluously. Instead, it's a good term, because it takes something that would be faint in terms of intensity and increases the intensity. It amps it up and allows us to see dim light from far away. All we need to do is find light that's behind a big gravitational source. And there's lots of examples of it. Okay? So the multiple images formed by gravitational lensing are wonderfully well demonstrated here in this picture and in this zoomed in region of the picture. We see a closer galaxy here, and then we see a distant galaxy multiplied 4 times due to the lensing effect, the three-dimensional bending of light due to the gravitational influence of the matter that's between us and the source of the light. Remarkable, isn't it? Here we see gravitational lensing smeared out, but still kind of taking that same circular look, smeared out over space. Okay? And this is pretty cool. We can actually kind of triangulate the position of where the light came from because it was bent due to some gravitational source. Then we can put it back together and actually, it's blurry, but we can reform the original image. We can show the shape of the original galaxy. This irregular, perhaps almost approaching spiral shape of the original galaxy, stretched out and bent due to the lensing effect of the warping of the space-time continuum due to gravity, as predicted or hypothesized in Einstein's general theory of relativity and experimentally proven again and again. Okay? So that's the technique. And gravitational lensing is pretty amazing. But the result of the technique is the collection of data that allows us to map the universe itself. And people like Margaret Geller have worked on this, have made it their life's work to collect all that data and form these maps of the universe. And what we find is something that looks like this, the large-scale structure of the universe. I'm going to zoom in on this a bit. And the scale here is measured in redshift. We could convert this to light years using Hubble's law, okay? And, well, Hubble's law and then the very notion of redshift and how it relates to the speed of light, okay? So we could use the combination of Hubble's law and the formula for redshift and convert this z value to distance. But regardless, we're looking at about 12 billion years. And what we see are clusters of galaxies. You can think of every individual pixel being a galaxy. And we see these clusters of galaxies, and then we see regions without galaxies. We see the voids, and we see the clusters. And that's the structure of the universe. Truly, it is the structure of the universe. And we can account for the colors by accounting for the redshift. We can get some idea that we're looking at regions that are younger, and therefore look different because they're younger, not because they're further away, right? So we can kind of extrapolate the evolution of galaxies, right? And we even see that a little bit. We kind of, if you squint your eyes, you can kind of see how the closer regions, the ones with a smaller redshift value, are maybe a little bit more well-defined, have denser regions of galaxies, but then at the very edge, where the redshift value is very, very large, where the distance is incredibly large in billions of light years, and the galaxies we're looking at are younger, have only existed for a shorter amount of time because they are closer to the beginning of the universe, closer to the point of the Big Bang. Look what we see. We see more sort of spread out. See? Look at how it's less dense. We see lower density. Okay? And we see perhaps less well-defined voids, and we see lower density. So we've seen a trend of galaxies clustering together and leaving the voids emptier. Fascinating. Here's how astronomers collect such remarkable surveys of the sky to get the large-scale structure of the universe, using telescopes like the Sloan Digital Sky Surveys telescope shown here, right, in the mountains of Sacramento Mountains in New Mexico. And here is an astronomer working on an array of fiber optics for collecting huge amounts of data very quickly and then using computers to process that data. Okay, so let's shift gears again. And let's move on in our further study of the universe to dark matter. We've touched on dark matter a couple of times. But why come back to it? Well, because first of all, we talked about gravitational lensing. And it turns out that dark matter ends up being one of the explanations, or you could even think of conveniences, to make gravitational lensing as effective as it is. Okay, so hold that thought. Furthermore, we've seen dark matter because we've talked about the rotation of spiral galaxies and how they spin faster than they should, especially on their edges. And if we even want to understand the clustering of galaxies itself, the trend that I showed back here to more evenly spread out, to more tendril-like and clustered in terms of the overall structure of the universe composed of galaxies, then we need dark matter. And we'll use it for one other explanation as well. And you might think, oh, this is convenient, but you have to understand that dark matter is the only explanation, because these phenomena are not just quirks in our data, they're strong trends, and there is no way to explain them other than the explanation that there's a lot of extra matter in the universe that doesn't interact with light, hence we call it dark matter. It can't radiate light, it can't absorb light, which means it can't radiate heat or absorb heat as far as we know. Therefore, it is energetically separate from the rest of matter and must be composed of particles that are not like any of the particles we've discovered up to this point, like neutrons and protons and electrons, or even the building blocks of those more common particles. So that's dark matter, whatever it may be, and we don't know, and it's amazing, and it's an active area of research and study. So let's go over the evidence of dark matter, and hopefully I'll make it clear, and I've already started to make it clear, why we would talk about it in the context of a chapter on galaxies and the evolution of galaxies. But as we see, this is a spiral galaxy. This is observed data at a distance from the galactic core of the rotational velocity of the galaxies, or excuse me, of the stars in that galaxy. And we see that the stars are moving much faster than we would expect, and that's because there's extra matter outside of the galaxy, which is dark matter. So we see spiral galaxies are surrounded, they are enveloped in dark matter. That's the only explanation that we have in terms of why spiral galaxies spin as fast as they can. Furthermore, when we look at the gravitational lensing effects, see this circular bending light? That's gravitational lensing, as we saw before, of light sources like early galaxies that are behind this closer cluster of galaxies. And when we calculate the effects of the gravitational lensing based on a theory that we've experimentally confirmed many times, Einstein's theory of general relativity, we find that the bending can only be explained if there's a lot more matter than the light would suggest. And we already acknowledged there is a light to matter ratio, and there's matter in galaxies that we can't account for just because it's darker molecular gases. But even that doesn't come close to explaining the matter that must be causing the extreme effects of gravitational lensing. That's why we've realized that there's actually sometimes 10 times more matter than we can see explained by stars and interstellar gas. And the only explanation is huge amounts of dark matter that we think primarily surrounds galaxies rather than permeates it. And that's, like I said before, it envelops the galaxy. Further evidence of dark matter is hot gas. And you might say, well, dark matter doesn't interact with light. How does it make things hot? It doesn't, not directly. Because dark matter, as far as we understand, neither absorbs nor radiates light, thus neither absorbs nor radiates heat. But it does exert a gravitational pressure because it is matter. So that causes things to become more pressurized. And if a gas, like interstellar gas, is more pressurized, then it's hotter. And these gases can be very energetic, very low density, but very energetic. And we see that again and again. We look at interstellar gas, even intergalactic gas, the incredibly low density gas that populates the space between galaxies. And we see it emitting X-rays. Why? Because it's much more pressurized than we would expect, because it's being impeded upon, it's being pushed in by huge amounts of dark matter that surround galaxies and even surround clusters of galaxies. So if you don't have the image already, think of dark matter as huge clouds that surround galaxies, that exist like pushing hands of force, pushing down on all the galaxies that radiate light that we know of as ordinary matter? Because the dark matter would not be able to enter the galaxy. Because if it can't radiate energy away, it can never condense. Dark matter is stuck in a perpetual state of early universe conditions. It's stuck like the very first gas that collapsed into forming the very first stars that formed the very first tiny galaxies, like the galaxy that was only 800 light years across, that we discussed, that was over 12 billion light years away. That never happened for dark matter. Dark matter was never able to collapse and start forming galaxies. There's no such thing as dark matter stars or dark matter clouds of various densities. Because if it can't radiate energy away, if it can't exchange energy via light, then it's stuck in one state. So on the one hand, dark matter is so mysterious because we can't figure out what it's made out of, and we can't experience it in our own solar system because it doesn't permeate galaxies. At the same time, it's incredibly simple because it's just one type of matter that can't collapse. So it never interacts in any way. It's stuck in one state, in one dispersed low density state, but in huge quantities, pushing on galaxies, heating up interstellar gas, heating up intergalactic gas. Okay, so let's wrap up with a few final topics. Here we see some dwarf galaxies near our own galaxy that are eventually going to crash into the Milky Way. Here is a model of that idea of those Milky Way galaxies, of those dwarf galaxies crashing into the Milky Way, stimulating star birth and star production, stimulating hot interstellar gas. And we bring this up because this seems to be an ongoing phenomenon. Smaller things crashing into bigger things, smaller galaxies crashing into bigger galaxies. And indeed, that appears to be really the most compelling evidence of what's been happening this whole time, and driven by dark matter, and visualized via gravitational lensing. But the overall trend, the idea that we started with in this lecture, is that smaller irregular galaxies have formed, have merged, have crashed together to get to the larger galaxies and the types of galaxies we see today. And that leads to the model of the overall universe, that over billions of years, from the very beginning, the Big Bang, there was small clusters that led to larger clusters, and then led to more condensing and greater voids and bigger mature galaxies. And so that means that at the very beginning, the very proto-galaxies, the most primordial galaxies that we wouldn't even call galaxies, they must have been like globular clusters. And that word, globular clusters, is the word we use for the little pockets of stars that exist in the halo of the Milky Way. Those little pockets of stars that formed when the intergalactic cloud was condensing and speeding up under conservation of angular momentum and energy to form the spiral galaxy that is our home galaxy, that is the Milky Way. And those globular clusters, they formed, and we still see them today, composed of only old stars stuck in the halo outside of the elliptical plane of the galaxy. Well, that idea, something like globular clusters, is probably how it all started. That was probably the first conglomeration, the first bringing together of stars that the universe ever saw, and the very first stars that were ever formed when gas collapsed under the influence of gravity. Collapsed because it could radiate light energy away, leaving the dark matter behind, uncollapsed, separated. And that really brings us to this understanding of the beginning and how we even got to discussing galaxies, and ideas about how we could go from smaller clouds to galaxies and then eventually to clusters of galaxies, how that was just a natural progression. And the reason we leave off on this idea is because it's what we started on in this lecture, how we started on the idea that galaxies are constantly interacting, crashing together, and because it gives us this idea that it started with very small pieces, small clusters of stars that then became small galaxies, irregular primordial galaxies, and so on. And in doing so, it sets the stage for our next topic, for our next lecture, which is going to be, well, that's great, But what came before that? And of course the answer will be the Big Bang. Well, I hope you've enjoyed this lecture on the discussion of galaxies. I hope it has been interesting and informative. Thank you so much for watching.